Okay, thank you for joining us as we look at another lesson involving vectors. And for this lesson, we're going to be looking at distances and angles using vectors, right? The approaches that are going to be seen in this lesson are listed above, right? But we're going to focus on finding the shortest distance between some points, between lines, and between planes, as well as finding angles at intersections involving planes or lines and planes. So let's have a look real quick. This is important to understand that if we consider planes intersecting, right, to be able to find the angle between planes intersecting, we actually just need to find the angle between the normals intersecting. And the reason for that is the geometric relationship of the quadrilateral that is formed. All right, we know the normals are perpendicular. We know that the normals are perpendicular to their planes, and so the sum of those angles is 180 degrees, and that means that the sum of the other two angles formed in the quadrilateral also has to be 180 degrees. So if we recognize that we have these supplementary angles, alpha and theta, where alpha represents one of the angles between the normals and theta is the supplement, then we can visually see that alpha and theta must then also be related within the representation of the angle between two planes. All right. We can also, like I said, look at the intersection between a line and a plane, but we'll review that in just a little bit. So if we want to find the radian measure of the acute angle between plane 1 and plane 2, we just need to find the angle between the normals. All right. So to do this, we need to find the angle between normal 1 and normal 2. There are a variety of ways to do that, but one way to do it is by recognizing that normal 1 dotted with normal 2 must be equal to the magnitude of normal 1 times the magnitude of normal 2 times the cosine of the angle between them. Okay? So for this particular problem, we have 1, 2, and -2 as the normal vector for our first plane, and we have 2, -3, and -6 as the normal vector for our second plane. And we know that that must be equal to the magnitude of our first one, which will be 1 plus 4 plus 4, right, times the magnitude of the normal vector of the second plane, which will be 4 plus 9 plus 36, right, and times the cosine of theta. So that tells us that the cosine of theta must be equal to, all right, if we want to use our calculator to find the dot product, that's fine to do. All right, we'll go to our calculation, go to our toolbox, come down to matrices and vectors, and head down to vectors, and we can say, hey, let's find our dot product. Back to our vector piece in the toolbox. All right, and I can come up and say, hey, let me add a new matrix or a vector, and I'm just going to write the row vector for my first one, which is 1, 2, and 2, right? And my second, if I wanted to, I could actually do Shift E to the X to start my new matrix, and I would have 2, -3, and -6. All right, and it's always important to double check that you have everything set up correctly, and we notice, oh, it should be 1, 2, and -2 for my two vectors, and I'm looking for this dot product, and so it gives me a dot product of 8. So the numerator is 8, and the denominator is the square root of 9 times the square root of 39. Okay, so if I want to be in radians, I need to make sure that my calculator is in radians. And so now I'm going to look at my inverse cosine. All right, now I'm going to look at my inverse cosine of 8 divided by the square root of 9 times the square root of 39. And so that gives me my particular angle. And in this case, that particular angle is approximately 1.13 radians to 3 significant figures. Remember, if it doesn't tell you, you need to give the answer to 3 significant figures for work with the International Baccalaureate. Okay, so that's all you have to do to find the angle between two planes. Just find the angle between the two normals. Okay. If I want to find an angle between two lines, same approach for finding an angle between two lines. Angle between two lines is just going to be using the dot product. So here we want the degree measure, and what's going to be important is that we can recognize the form of our equation. So we'll say my first line has a 0.5, -1, 4, right? And it has directionality 3, 4, 12. My second line has the point 4, 5, 20. And remember, 5 minus y we want to rewrite as y minus 5 divided by -1. So that's why I have a point of 5. And then make sure I change my parameter. And the directionality is 2, -1, -2. All right. So that tells me then that if I want to find the angle, I'm going to have that the cosine of the angle between is going to be the dot product of my two directional vectors, 3, 4, 12, 2, -1, -2, right? All divided by the magnitude of 3, 4, 12. That's going to be 9 plus 16 plus 144, right? And that's going to be 4 plus 1 plus 4, right? I want this to be to the nearest degree. So if I need, I can find my dot product without using the dot product feature. I can just remember that it's going to be the sum of the products in the x direction, y direction, z direction. So I'm going to have 6 minus 4 minus 24. All right, so I have 6 minus 4 minus 24, and that's going to be -22. And in the denominator, 9 plus 16 plus 144 is 169. So I know the square root of 169 is 13. And 4 plus 1 plus 4 is 9. And so I know the square root of 9 is 3. All right, so I have the cosine of theta is going to be given by this value. Because the numerator is negative, I know that theta is going to be obtuse. All right, if you're not specified whether it's going to be the acute or obtuse angle, provide what results from your mathematics. All right, so in this case, it's going to be an obtuse angle. So we can go inverse cosine of -22 divided by 13 times 3. And that gives me a radian measure and the 2.170, and so it already is calculating my particular value that is going to be an obtuse angle. And if I take that number and I multiply by 180 and divide by pi, that'll give me my degree measure, and it needs to be in this case to the nearest tenth of a degree. So that means that theta is approximately 124.3 degrees. All right. Angles between planes, angles between lines, the approach is the same. The only difference is that with planes, you're going to use the normal vector. Okay. Now, Let's look at another example. And let's see here, we have two equations. We have the equation of a line and the equation of a plane. And we want to find the common point of intersection, and we then wanted to find the degree measure of the acute angle formed between the two equations. So we should recognize that we have a line, and we should recognize that we have a plane. All right, so what's going to be the relationship? Let's come back up here. And if we have a line intersecting with a plane, the angle between the line and the normal vector is going to be complementary to the angle between the line and the plane. And that's all we need to remember, that there's going to be that complementary relationship. So let's look to do that work. So first we want to find the common point of intersection. To find the common point of intersection, we need x, which is going to be -3 plus 2 lambda, and y, which is going to be 5 plus 4 lambda, and z, which is going to be, let's see here, if 3 times z plus 1 all over 2 was equal to my parameter, then I know that z is going to be, let's see, 2 divided by 3, so 2/3 lambda minus 1. To find that point of intersection, the x, y, and z must work within my plane so that the line and the plane are at the same point. And so I can say 5 times -3 plus 2 lambda minus 5 plus 4 lambda plus 4 times 2/3 lambda minus 1 has to equal 2. If I come to my equation solver, I can put that into my calculator, plus 2, and I'll just use n as my variable here, minus parentheses 5 plus 4, use n as my variable. Doesn't really matter what letter you use, as long as you're consistent within the context of your work. And then I have 2/3, right, my variable, minus 1, and that needs to be equal to 2. All right, if I solve that equation, it gives me lambda is equal to 3, and if lambda is equal to 3, therefore my point of intersection is going to be, let's come back to my calculator, is going to be -3 plus 2 times 3, right? And 5 plus 3 times 4. And lastly, 2/3 times 3 minus 1. And so there we have the coordinate of our point of intersection. You could certainly substitute that point into your plane and or the equation for your plane and double check that the solution is consistent, and it is. So we have the point of intersection. We know that they intersect, so we know that there's going to be an angle between them. And how am I going to find the angle? Like we said, we just need to look at the cosine of the angle is going to be based on the dot product of the directional vectors. And so we have 2, 4, and 2/3, right? 2, 4, and 2/3 for my line. We've got 5, -1, and +4 for my plane, and then all over the square root of, all right, let's go ahead and go 2 squared plus 4 squared plus 2/3 that quantity squared. Okay, and we make sure that it's written correctly, and so it gives us 184 over 9. All right, and the other one would give us 25 plus 1 plus 4. If you need to use your calculator and it's calculator active, you can. Okay, so remember, theta is going to be the angle between, right? The theta is going to be the angle between the normal and your line. So if we want the angle between the line and the plane, then I could either say 180 degrees minus theta, or not 180 degrees, excuse me, 90 degrees minus theta, if I'm working with an acute angle, is going to be the angle needed. Right? But you could also use the following relationship. And that relationship is that the complement to the cosine is going to be saying that, hey, my sine of theta is going to be 2, 4, 2/3 dotted with 5, -1, 4 all over the square root of 184 over 9 times the square root of 25 plus 5. That would be the square root of 30. Okay, so we got to be careful about which angle that we are talking about and the angles that we care about. And so I would actually say the sine of alpha, and we'd say alpha is going to be the angle that we need. So let's go ahead and find that dot product, or that sine ratio. So 2 times 5, right? And then 4 times -1. Oops, let's make sure we have 2 times 5 plus 4 times -1, right? Plus 2/3 times 4. And that gives me 26/3. And I need to divide 26/3 by the square root of 184 over 9 times the square root of 30. And I got to be careful about where my square root sets up. So square root of 30, right? It's not one square root under the other. And let's go shift inverse sine of that number. That's going to be radians times 180 divided by pi. And so I get that alpha is approximately 20.5 degrees. And I need to make sure that I round that, because if I'm going to be correct to 3 significant figures, I need to make sure that I am correct to 3 significant figures. Okay, let's look at the same approach but using the cosine. So our numerator would have been the same, right? That 26 over 3, right? That fraction is all going to be the exact same. And then we have that particular value, and we say, well, what's going to be the inverse cosine of that number? All right, and if I take that and I multiply by 180 and divide by pi, that gives me that particular angle, but I know I need the complement to it, and so I can see, let's see if I could get up there, that I get to that exact same angle. So the angle that I care about is going to be that angle of 20.5 degrees. You want to be careful. If you use the sine approach, that's fine. Be careful with your notation. If you use the complementary angle approach, that's fine. Just be careful with your notation. Okay? You cannot speak to how much these figures really help you understand finding the intersections between planes, right? Which is just the intersection between the normals, and finding the angle of the intersection between a line and a plane. All right. Thank you very much for your time. Make sure you come back to get help with the other problems as you need.